right, we got our machine learning toolbox in hand, models, loss functions, training loops. Now let's focus on a specific model, logistic regression. Why logistic regression? Because it's the mathematical twin of a single artificial neuron. If we understand logistic regression deeply, the leap to neural networks becomes much smaller. So, in this section, we'll revisit how logistic regression works, what it models, how it predicts, and what loss function it uses. This is the Rosetta Stone moment. Once you see the connection, the rest of the neural net architecture will start to make sense. Here's our updated location on the map, section 3, logistic regression to ANN. This is where things start looking familiar to anyone who has done even basic classification tasks in machine learning. But keep your eyes open. We're not just reviewing. We are reverse engineering how a neuron works step by step. So before we get to artificial neural networks, we need to pass through logistic regression. This model is the direct ancestor of a single neuron. So let's warm up with a quick refresher on how it works, classification, the sigmoid function, and how we measure error. Imagine this, you're a doctor and a patient walks in with a chest pain. You've got data, age, cholesterol, blood pressure, heart rate, chest pain, symptoms, etc. Your task, predict whether this person has a heart disease, yes or no. That's a classification, a binary output based on multiple inputs. Looking at few samples from the dataset, each row represents a patient. Features like age, sex, chest pain type, and cholesterol form the input. The final column, AHD, tells you if the person has heart disease, yes or no. That's your label. And in supervised learning, the model tries to learn the mapping from input to label. The labels are, yes, patient has heart disease, no, they don't. It's important to note that these aren't numbers, but we later convert them into zeros and ones so we can work with them mathematically. Logistic regression learns to assign a probability to each input. How likely is it that the output is 1? Here's the full model. Step 1, apply a linear transformation to the input. H is equal to beta 0 plus beta 1x. Now, even though we often call this a linear transformation, it is technically an affine transformation because it includes a bias term, beta 0. That bias shifts the output without changing its direction, and it is important for flexibility in feeding data. Step 2, pass through the sigmoid function to squash it into probability. So sigma h is equal to 1 over 1 plus exponential of minus h. The result is a number between 0 and 1, which we interpret as the probability that the output is 1. If it's close to 0, the model predicts no. If it's close to 1, it says yes. Okay, let's put it all together. We start with a linear combination of the input, that's the h value. Then we feed it through the sigmoid function, which acts like a soft gate, squashing the output into a number between 0 and 1. That number is our predicted probability that the label is 1. This setup, linear transformation, followed by nonlinear activation, is the core idea behind not just logistic regression, but also neural networks. So how do we know if our model is doing well? We use a loss function, a way to measure how wrong the predictions are. In linear regression, we use mean square error, the average of the square differences between the predictions and the actual values. It works for continuous output, but not for classification. Why? Because probabilities don't behave like nice straight lines. In logistic regression, we use binary cross-entropy. It is designed specifically for binary outcomes and probability outputs. The formula may look messy, but the idea is simple. If the true label is 1, we want the predicted probability to be close to 1. If the true label is 0, we want it close to 0. Cross-entropy penalizes confident but wrong predictions, which makes it great for classification tasks. Up next, how this all connects to a neuron. You'll be surprised how little we have to change.